Hello everyone, this is Xu from Microsoft Research Asia. In this video, I will give a brief introduction about our paper. Our paper title is SPAN, a scalable log parser with feedback guidance. Let's start with some background about log data analysis. As is well known, logs record important system events and runtime status, provide first-hand information to developers and operators. Recently, many research efforts in automated log analysis have sprung up, such as log-based anomaly detection, failure diagnosis, failure prediction, and so on. Log parsing, as a critical prerequisite step, plays an important role in the most log data analysis approaches. Formally, log parsing is defined as extracting log templates and log parameters from raw log messages. The log template consists of some static keywords describing the system events, which are written in the login statement. Log parameters denote the dynamic variables that are filled in the placeholders of login statements during the runtime. Our goal is to distinguish the two parts and extract the structured format, as shown in the below table, from the raw unstructured raw log messages. Also, many log parsers have been proposed and achieved promising accuracy on public log data sites. This still face many challenges in real-world applications. It is because there is a huge gap between industry log data and the public benchmarks. We conducted an empirical study on the industry logs to reveal the characteristics of the real-world logs. Firstly, industry logs feature extremely large scale. Only for the single log sources in our study, there are about a few billion log messages generated every day on average. In addition, we also found that the log data is extremely imbalanced. The left figure shows the histogram of the number of logs with different templates. We can see that most of logs are concentrated on the top few log templates. Thirdly, new log templates will emerge continuously in production. From the right figure, we can see that the number of new log templates continuously increases due to the CI/CD paradigm. To deal with the large-scale imbalance and evolving industry log data, we propose SPAN, a highly scalable log parser with feedback guidance. Here is an overview of our log parser. It has two phases, offline training and online parsing. SPAN consists of four components, that is pre-processing, initial grouping, progressive clustering, and online parsing. Based on these specially designed components, we can achieve log parsing parallelization for large-scale and imbalanced log data. In addition, we also can incorporate user feedback into our model for involving problem. In the pre-processing stage, we first split each log messages into a series of tokens and do some basic log data cleaning. After pre-processing, initial grouping is used to group similar logs in a coarse-grained fashion. The goal of this step has twofold. On the one hand, we aim to accelerate the subsequent clustering process by dividing the original whole log data into similar fragments. On the other hand, the data partition also makes parallelization possible because we can execute the subsequent parsing process independently according to the disjoint log groups. Specifically, log messages with identical first K tokens belong to the same log group because the log messages with the same prefix tokens are likely with the same log template. Next step, we need to further divide log groups into more fine-grained log clusters to extract their log templates. In SPAN, we adopted progressive clustering. It iteratively partitions log messages into binary subgroups, form a binary clustering tree until a stop creation is satisfied. Obviously, stop creation is very critical. SPAN adopts a token saturation as the stop creation. We define the saturation tokens as those tokens that appear in all log messages within a group. We know a cluster of logs generated by the same log templates share many common tokens, which means more log tokens will become saturated. We can use this property to control the clustering tree dips. After clustering, the logs in a leaf node are likely to share the same log template. In the online parsing phase, each newly arrived log will first be processed and grouped, and then assigned into an existing log cluster based on their similarity. In previous sections, we have introduced the building blocks of SPAN and for offline training and online passing. Next, we will introduce how to achieve passing parallelization and user feedback incorporation based on our proposed passing architecture. As mentioned before, log groups generated by the initial grouping are disjoint. As a result, logs in different groups can be processed in a completely parallel manner during the online passing. However, due to the imbalance issues as introduced, the size of one log group can be several orders of magnitude larger than another log group. Consequently, the passing time of some log groups could be significantly longer than other groups. To solve this problem, we propose a log data scheduling approach. The core idea behind our approach is splitting some large log groups into multiple executors and merge multiple small log groups into one executors. The pseudocode is present in the algorithm 1. In this way, the workload of different executors tend to be balanced. As for incorporating user feedback, the core problem is how to leverage user feedback to decide whether a leaf node should be split into two child or not. As shown in the right figure, in each feedback round, SPAN recommends a pair of logs from the same log cluster. The users give the feedback about whether this pair of logs share the same template. The user feedback helps SPAN to decide whether to split the corresponding cluster into two child clusters. How to recommend the most valuable log pairs benefiting the models? SPAN makes a feedback query based on the metric, namely situation gain. The situation gain is the increment of the situation if we split a leaf node into two child leaf nodes. Therefore, a higher situation gain value donates the splitting the current leaf nodes has the potential to improve the accuracy of the mode and is worthy querying user feedback. We conducted extensive experiments on 16 public benchmark data sites to validate our log parser. In our evaluation, we follow a widely adopted metric, namely passing accuracy. We compared SPAN with 5 SOTA parsers and also implemented the 4 versions of SPAN as follows to conduct an ablation study. For the passing accuracy, the experimental results are shown in Table 1. From the table, we can see that SPAN-based significantly outperform other SOTA parsers. To measure the efficiency of our proposed method, we compared the execution time of SPAN with 5 baseline log parsers on 3 large log data sites. From this figure, we can see that concludes that SPAN-based outperform all existing log parsers, especially when the data size is very large. We applied SPAN feedback on the 3 log data sites with unsatisfactory passing accuracy regarding to all log parsers. We also implemented 2 baseline recommendation strategies to show the effectiveness of our proposed feedback mechanism. The first one is a random selection, and another one is selecting by leaf node size. We can confirm that all 3 strategies can improve passing accuracy with the increasing number of interactions based on our log passing architecture. It is easy to see that SPAN feedback, which is based on the saturation gain, achieves the highest accuracy gain compared to the other 2 baselines. We evaluated the effectiveness of our proposed log data scheduling method on the 3 largest log data sites. We run SPAN parallel with different number of executors and record the execution time for each data site. We can see that our proposed log scheduling method can significantly improve the passing efficiency. We also applied SPAN into log processing pipeline for Service X of Microsoft. The blue curve in the right figure shows that the passing accuracy declines with time if we don't introduce any feedback guidance. We activated the feedback process every month. The passing accuracy with user feedback is showing the origin curve in this figure. We can see a significant passing accuracy boosting in the 5th week and the next week after querying user feedback. In Service X, one of the downstream log analysis tasks requires all log data passed within 10 minutes. We show the log volume and the corresponding time cost in seconds for log passing in the right figure. SPAN only spent about 8 minutes on average to pass 13 million of logs generated in 10 minutes window. which fulfills the requirement of the subsequent log data analysis task. In summary, we propose SPAN, a highly scalable log parser with feedback guidance. A novel log data scheduling algorithm is proposed to improve the prioritization efficiency under the large-scale imbalanced log data. In addition, SPAN incorporates user feedback to achieve consistent good parsing accuracy for evolving log data. The experiment results show the SPAN achieves high parsing accuracy on average with high parsing efficiency, public log datasets, and the production logs. That's all about our work. Thanks for listening.